Now we will state and prove the main result of this section, which is the existence of regular conditional probability for regular spaces. Okay, so the statement will be a little bit more general than the setup we discussed before, namely the setup of the product space. So here we'll consider some abstract probability space omega with sigma algebra A and some probability measure P on it. So in particular, the case of the product space will correspond to when omega is equal to the product space x times y with the product sigma algebra. Then we consider some measurable space y with the sigma algebra y, which in the case of the product space would just be the second coordinate y. Then we consider some measurable function f from our probability space to y, okay, which in the case of the product space would simply correspond to the second coordinate. So the function on the product space would simply be equal to y in that case. And then finally we consider some sub-sigma algebra of our sigma algebra A on the probability space. So B is also a sigma algebra. And again, in the case of the product space, this could be the sigma algebra generated by the first coordinate x. Right, so namely it's all rectangles of the form B times y, where B is a measurable set, so it's a set in the sigma algebra X. And then in this setting we give the following definition of a regular conditional probability. So a regular conditional distribution or regular conditional probability of this function f given sigma algebra B is some function which we will denote here p f given b, and it's a function that depends on the measurable sets in y and the points omega in our space omega, right? And since it's a probability, it will take values in 0, 1, and the properties of this function will be that first, for all omega, if we view this as a function of the set, so let's say the first coordinate will be the set, for a fixed omega, this will be a probability measure on y. And second is that for any measurable set in the sigma algebra y, when we view this function for a fixed set A as a function of the second coordinate omega, it will be B measurable. And moreover, it's not just B measurable, but it has to be equal almost surely to the conditional expectation of the indicator. So this function viewed as a function of omega should be equal almost surely to the conditional expectation of the indicator that f belongs to the set A given the sigma algebra B. And our goal will be to show that when the space y is regular, then we can always construct this regular conditional distribution of this function f given a sigma algebra B. And of course, in the case of the product space when omega is equal to x times y, this regular conditional distribution of the second coordinate given the sigma algebra generated by the first coordinate, because it's measurable with respect to the sigma algebra generated by the first coordinate, right, it will depend only on the first coordinate. So again, we can view it as a function of x and a. And the properties above will be exactly the properties of the transition kernel. And the fact that for a fixed set A, the definition is equal almost surely to this conditional expectation of the indicator, okay, we check that this implies exactly the Fubini representation that we want, right? That namely the indicator of any rectangle can be written as an integral with respect to the transition kernel, and then integral with respect to the marginal on x. Okay, and once you have that representation for rectangles, you get a general Fubini theorem, just like in the construction of the product measure in real analysis. Okay, so what remains is to prove the following theorem. That if our space Y is regular, so again, complete separable metric space with its Borel sigma algebra, then the conditional probability of F given the sigma algebra B exists, and moreover it's unique almost surely with respect to the probability measure restricted to the sigma algebra B. In other words, if you have two regular conditional probabilities, they can differ only on a set of measure 0, and that set will be in the sigma algebra B. So now let's prove this result. So first of all, the separability of the space will be used as follows. That we'll take a countable collection of sets that generate our sigma algebra. So let's call it Y prime be a countable collection of sets, measurable sets, such that our sigma algebra Y is generated by this countable collection Y. Now, of course, because our space is separable, one such collection that we can take is simply take a dense countable set in our space and then consider open balls of rational radius around those points. Using those open balls, you can, of course, generate any open sets, and as a result, the Borel sigma algebra. Then let C be an algebra generated by this countable collection Y prime. And again, let's notice right away that this is a countable collection itself. Right, since the algebra generated by this collection Y simply consists of any finite set operations. So you take finite intersection, union, and complements. And so you can keep adding these sets in collection Y prime one by one, and as a result, this C can be written as a countable union of actually finite collections of sets. Okay, so in other words, separability allows us to start with some countable algebra that generates our sigma algebra Y. And then we will use completeness as follows. So since Y is complete, we can appeal to Ulam's theorem. Namely, Ulam's theorem tells us that the probability measure on a regular space is regular, and any measurable set can be approximated by compacts from below. Right? So for any measurable set in our sigma algebra, there exists a sequence of compacts, let's say increasing sequence of compacts inside our set C, and let me put the label C on these compacts to indicate that this corresponds to this particular set C, such that the probability that our function f takes value in this compact converges to the probability that f takes value in C, okay, when n goes to infinity. And so in addition to this countable algebra, we also want to include, or we also want to consider these compacts that approximate sets in our algebra. So we will enrich our collection C and now denote by D an algebra generated both by this algebra C and these compacts K and C for all n and all C in this algebra C. Okay, obviously this is still a countable collection of sets, so this algebra generated by a countable collection of sets will still be a countable algebra. And then, since we want to construct this regular conditional distributions for all sets in this countable collection, of course we just define this conditional probability of the set D as a function of omega by what it should be, namely by the conditional expectation of the indicator, given the sigma algebra B. Okay, so this is a function of omega, and so for each set in this specific countable collection, we just fix the regular conditional distribution to be any particular version of this conditional expectation. Okay, so we just fix any version of this conditional expectation. And then our goal will be to show that this definition on this algebra can be extended to the probability measure on the sigma algebra without violating the conditions in the definition of regular conditional distributions. Okay, but in order to do this, let's just notice the properties that we'll need for that. So once we take this particular definition of this regular conditional probability on the sets D, let's notice that they satisfy some basic properties implied by this definition. Right? Namely, for all D in this collection, of course, this will be non-negative function almost surely, right? Because the conditional expectation of the indicator, which is non-negative, will be non-negative almost surely. 2 is that when you consider the whole space, so in other words, you are taking conditional expectation of 1. It will be just equal to 1 almost surely, or we simply can set it to be equal to 1. And for the empty set, when this set is empty, that's taking the indicator will be equal to 0, and so conditional expectation of 0, you can just take it to be equal to 0. Okay, almost surely, but here we can just take for all omega. Then we also have finite additivity for any finite collection of disjoint sets. So if you take any k and you take any disjoint sets d1, dk in this algebra D, then conditional probability of their union, right, because it's defined via the conditional expectation above and conditional expectation is linear, this will be equal almost surely to the sum of conditional expectations, which we call these conditional distributions of those sets. Okay, of course, this is again almost surely because linearity for conditional expectation holds almost surely. And then the last property is just the consequence of the fact that compact sets approximate our set C. So for any C in the algebra C that we define first before we define D, since we chose compacts that approximate these sets, of course, the almost sure convergence implies almost sure convergence for conditional expectations, so we also get that these conditional expectations for the corresponding compacts will converge monotonically to this conditional expectation for each of the sets C. Okay, so all these statements A, B, C, and D are just consequences of the properties of conditional expectations. Now, when we look at this set of conditions here, there are countably many of them, right? Because there are only countably many ways we can choose these sets D or these finite disjoint collections in algebra D. So here we have countably many conditions, and as a result, all these almost sure statements will hold everywhere except some exceptional set of measure 0. So there exists a set N, which will be, by the way, in the sigma algebra B, because all the statements above are written in terms of functions which are B measurable. It will have probability 0, and the conditions A through D will hold for all omega outside of this set. Okay, so if we take any omega outside of this set, we want to show that the above conditions or the above properties A through D allow us to extend conditional probability that we defined on some countable algebra to the entire sigma algebra. Right? So we will show that first, this definition above can be extended automatically from our algebra C to a probability measure on the sigma algebra Y. Okay, and of course this will be done by Carathéodory extension theorem. Now this will be done for this non-exceptional omega, so omega outside of the set N. So in other words, for omega where all the conditions above A through D hold, and then for omega in the exceptional set, we'll simply define this probability measure to be whatever we want. So the definitions of regular conditional probability will not be affected if we modify it on a set of measure 0. Okay, and then 2 will show that this extension also satisfies the property that we want now for all sets in this sigma algebra Y. Right? So in other words, once we extend the definition of this regular conditional probability, it will still coincide almost surely with the conditional expectation of the indicator for any measurable set A. So now we will have a regular conditional probability which is both a probability as a function of the set, and it also satisfies this property that it's equal to the conditional expectation. Okay, so now we'll focus on proving these two properties 1 and 2 for any point omega not in the exceptional set, so in other words under the conditions A through D. So first of all, in order to use Carathéodory extension theorem, we want to show countable additivity on the algebra or continuity of the measure on the algebra. And in fact, it's enough to show continuity at the empty set, okay, on the algebra. So more precisely, we have to consider a sequence of sets in this algebra C such that they decrease and their intersection is an empty set. And then what we want to show here, so this is a question mark, that this conditional probability that we define on these sets, right, will converge to 0. Okay, and here again we assume that this omega belongs to the non-exceptional set, and in particular we can use the properties A through D. And actually we already implicitly here using these properties A through D, because the fact that these quantities decrease, this is actually a consequence of the assumptions A through D. Right? Namely, the first assumption that these are non-negative on omega outside of the exceptional sets. And we had a third property, which is a finite additivity. right? So in other words, if we represent the set Cn plus 1 as a union of two sets in this algebra, we will have an equality, right? Because the second term is non-negative. So these are in fact decreasing by the above properties, and we want to show that they are decreasing to 0. And we will show this by contradiction. So because otherwise, if they do not go to 0, that means that all these quantities are separated from 0. So there is some strictly positive delta such that all these are greater or equal than this delta. And then we will use the last condition that any set in this algebra can be approximated by compacts from below with arbitrary precision. So as a result, we will take a compact Kn such that this regular conditional probability for the difference Cn minus Kn is as small as we like, so we'll take it to be less than delta over 3 to the n. And then we can use again the properties above, such as finite additivity on this algebra, to show that when we look at this conditional probability on the intersection of these compacts from 1 to n, this will be close to the intersection of the sets C. So this will be greater or equal than the same quantity with intersections of the sets C1, Cn. Okay, and the error here will be just adding up these errors delta over 3 to the n. So this will be minus the sum up to n of delta over 3 to the I. And again, I'm skipping the details here. This is kind of a standard calculation that you would do with probabilities, showing that the intersections approximate intersections if your sets approximate well. And of course, in that calculation, we only use finite set operations here. So finite additivity above and the monotonicity or positivity is enough to show this inequality here using again the properties A through D and assuming that our omega is in the non-exceptional set. And then, of course, the sets C, they are decreasing, so the intersection is actually equal to the set Cn. And the sum here is less than delta over 2, and since we assume above that these quantities here are greater than delta, the difference will be greater than delta over 2. And in particular, this implies that this intersection here, so let's denote it by Kn, it will be non-empty, again by the condition B, because if this set was empty, this conditional probability should be 0. And since it's not 0, this set is non-empty. And finally, because the intersection of compacts is also a compact, and now these compacts Kn, they are decreasing since we are intersecting them. And moreover, recall that these are inside the set C, so this is inside the set Cn, which is decreasing to an empty set. Right? We get that these compacts Kn are decreasing to an empty set, okay, which is a contradiction. Okay, we know from real analysis that a decreasing set of compacts has some non-empty intersection. And so as a result, this conditional probability that we define first on the algebra for any non-exceptional point omega by Carathéodory extension theorem can be uniquely extended to a probability measure on Y. Okay, and again, this was for all points outside of this exceptional set. Now, for points in the exceptional set, we can simply take this conditional distribution to be any fixed probability measure. Okay, for example, concentrated on some fixed point. And so this function that we constructed so far has the properties that we want. It's a probability measure as a function of the set for all omega, and for any fixed set, it's B measurable with respect to omega. Okay, and so what remains is to show the second claim above, that once we extended it like this, it is still equal to the conditional expectation of the indicator for all sets. Okay, but this statement is an immediate consequence of Dynkin's theorem, for example. So if we consider all sets A such that the property that we want holds, namely our extension on that set, okay, viewed as a function of omega, is equal almost surely to what it should be, namely the conditional expectation of the indicator that F is in that set given sigma algebra B. Now, this collection of sets is obviously a lambda system because both sides here are countably additive, right? The conditional expectation on the right-hand side and the probability on the left-hand side are countably additive, so this almost sure condition will be preserved under taking countable disjoint unions. But on the other hand, just by construction, this equality was ensured on the algebra, so it contains this algebra C, right? And so then Dynkin's theorem implies that actually it contains a sigma algebra generated by C, which is actually the entire sigma algebra Y. Okay, so by Dynkin's theorem, okay, this is actually equal to the sigma algebra generated by C, which is the entire Y. So in other words, this extension, this regular conditional distribution, it satisfies now all properties that we want for all measurable sets. Okay, so that proves the constructive part of this theorem. And then finally, we just have to mention about the uniqueness. Namely, suppose that we have two versions of this regular conditional probability. So we have one version and we have another version. But we know that, of course, because these two versions, P and P prime, are by definition equal to the conditional expectation of the same indicator, they have to be equal almost surely for any fixed set C. So in particular, for any set C in the countable algebra C that generates our sigma algebra Y. Okay, but if this is true on countably many sets, then you can just take a union of these exceptional sets, and of course this equality holds for all omega on the set of measure 0 simultaneously for all these sets, right? So this here holds for omega on some set of measure 1. Okay, for all C in this algebra simultaneously. But of course, the probability on the algebra determines the probability on the entire sigma algebra, so of course then we know that this equality for all such omega, this equality should also be true for all measurable sets. Okay, and so we have this statement again for all omega on the set of measure 1 for all measurable sets, and that's exactly what we want, right? So there is maybe an exceptional set which is in the sigma algebra B of measure 0, and outside of that set these two conditional distributions should be equal as distributions for all omega outside of that set. And so this finishes the proof of this theorem and this section on regular conditional distributions.